My name is Richard. I'm joined here today by Toby and Eloise, and I'd like to talk to you about some real-time stuff. How many of you saw Jensen's keynote yesterday? Wow, pretty much everybody. Yeah, so I borrowed a few slides from Jensen just to set the stage for what this real-time stuff is all about. So USD, it lets you collaborate. And with USD, data is kind of at the center. So if you're around the edge, you can work in parallel, and then it provides you a way of composing all your work into some final product, like a final animation. But Jensen mentioned something else that we've been doing with USD. So for the past 5 years, we've been extending USD to do real-time physics-based systems, and especially for new industrial applications. So what is Omniverse? Now, Jensen said Omniverse is not a tool. It's a tool for connecting tools. But let's think about this extension of USD to real-time applications. Could you really make an application that could do authoring and composition for the movie industry on one end, and making digital twins and real-time simulators and AI driving simulators on the other hand? And the answer is pretty much no. So I take what Jensen said just a stage further. It's not just a tool for connecting tools, but it's also a toolkit for making applications out of components. So you can have one application factory explorer for making digital twins, and you can have USD Composer for composing USD. And this has been working out pretty well. Omniverse is widely used across the world's industries. You can see some examples here. Here is an application. So the application on the left, it's writing some data to USD, and then the renderer is reading it at some later time. And if the application writes something new that the renderer doesn't understand, it doesn't matter, the renderer can just skip over it. So it's a really loose coupling. So suppose you want to do what I mentioned to you earlier about making different applications for different use cases in different industries by gluing together different components. How should those components communicate? So one option you could use is the components could call each other's APIs. But that's completely different. That's a really strong coupling. Because if one component changes, you might have to recompile some other components. And the other components, they could be from different companies. So you might not even have a source code. So USD shows us the alternative. USD shows us the way, and that is communication through data. So not only can applications communicate through USD, but also components within the same application can communicate with USD and the renderer. But as you can imagine, that's potentially quite a lot of USD communication within one application. And I was mentioning earlier to you these real-time applications. So in the traditional authoring pipeline for movies, where the final product is an animation, the composition, it's kind of occurring at a human timescale. It's all about humans collaborating and humans composing their work to a final animation. And because it's on a human scale, it can happen asynchronously, and it can happen non-real time. But if your final product is one of these new applications, one of these new industries, like making a digital twin or a driving simulator, the whole thing has to run in real time. So this thing here that you can see, it's a real-time loop. And you've got if it's 60 hertz, then you've got 60 milliseconds between someone pressing forward and you actually rendering the animation. And so that puts a lot more stress. If you are using USD for all your communication between the components, that puts a ton of stress on this communication. The communication, to meet a 60 millisecond budget, your communication might have to be in the sort of nanoseconds or microseconds. And so this is where Fabric comes in. So you can think about Fabric as being like a cache that's in front of the USD stage, just as a CPU cache is in front of the main memory. So you can communicate the real-time data in USD formats or in other formats through Fabric as if you were talking to a USD stage. Now, you're all here at USD Day, and also we've already written, and other companies have written, a ton of Omniverse components, we call them extensions, in USD. And so the API for Fabric has to be somewhat USD-like, so that people you've made your investment in USD, you can just get some extra real-time performance by using Fabric. So we made something called Usdrt. And it's USD-like. I'll show you exactly how USD-like it is on a later slide. Now, once you've made the choice to put your data in an optimized cache, you've got the choice about how you arrange the memory. And so what we've done is arrange the memory for two reasons. So one reason is, or one criteria, is to make it efficient to send it from the CPU to the GPU. So one of the things Fabric does, it lets you access the data on the GPU. But also, it's indexed so that you can do very fast queries like give me all the meshes or give me all the animations or whatever it is. We'll talk a bit more about that later. Now, I mentioned the real-time loop earlier and about how it might run at 60 Hertz. But actually, we've got some applications where you have a whole bunch of different iterative loops at different frame rates. And so we have a feature called Fabric Lanes, and Toby's going to talk about that later. So once you have reformatted your data into some vectorized, easily searchable format, one thing you can do with it is just render from it directly. And that's what we've done. We provide the Fabric scene delegate, and Alois is going to talk about that in a little while. So I started this journey about 5 years ago working on this real-time Fabric stuff, and luckily I accumulated this huge, this modestly sized team along the way. So I'd just like to talk a little bit about USDRT. So as I mentioned earlier, the goal of USDRT is to make a USDRT-like API in C++ and in Python to access the compose stage. Because Fabric, because most real-time work is happening on the compose stage. It's happening after authoring. But USDRT, it's not just a USDR-like API, because it also provides a bunch of extra features which are not in USD to give you the access to the extra performance that these special data formats give you. So how USD-like is it? I'm going to show you on the next slide. On the left, I'm going to show you USD and the same thing in USDRT. And how many differences can you spot? So the root of the include paths is about the same. The root of the include paths is different, and the namespace is different. But all the basics of USD, like USD stage, USD prim, USD attribute, exactly the same. We have this goal called pin compatible. It comes from chip design. A chip is pin compatible if you can just take a chip with one pin out from one manufacturer and just put it in the socket of another manufacturer. And there's some benchmarks there. It's pretty fast. Switching gears a little bit, I'd like to now just show you two examples of the features that we've added which are not in USD. So the first one is optimizing load time. So we're working on an application called Factory Explorer. And these factories are absolutely huge. It's like CAD data of a factory that someone's going to build. So it's got all the information in it that you actually need to make a factory, with bulldozers and construction workers and everything. And so when we loaded these files, we found that the load time was really slow. It's like 180 seconds just to load the file. And so when we profiled it, we saw, this is a cartoon of what we saw. So the gray rectangles here, these are the extensions. And the blue rectangles show the proportion of the extension which is due to traversal. So a consequence of this highly modular architecture that I mentioned earlier is that extensions have to find their own data. And so what you see a lot is the physics extension is iterating over all the prims in the stage, trying to find the physics prims. The renderer is iterating over all the prims in the stage to find rendering, and so on. And so it's pretty wasteful. You might iterate over 1 million prims just to find 100 physics prims or 100 cameras or whatever it is, 100 lights. So if you zoom in on one of these blue regions, it's just as you might expect in USD. It's just a traversal. Then you have an if statement. Is this thing that I care about? And just doing the traversal can take a huge amount of time relative to the actual amount of work you're doing to store the path to the thing you really want. So USDRT has an alternative. As I mentioned earlier, USDRT, it makes an index of the stage. It buckets prims according to their type. And USDRT provides a new API where the extension can just say, hey, give me all the physics prims, or hey, give me all the render meshes. And so Fabric, it just traverses the stage once. That's the first blue rectangle here. And then every subsequent call where you say, hey, give me all the physics prims or whatever it is, it can return in constant time because it's already bucketed all the data. And so you can see overall it was a lot faster. And in fact, the Factory Explorer, it went from about 180 seconds to 20 seconds. And that was the difference between the customer accepting it and not. So that was huge. There's one last feature of Usdrt I'd like to tell you about today. Now, the previous feature is in the currently released version of Usdrt. And what I'm going to show you next, it's not in the current version, but it's going to be released soon. So it's the same idea that I just showed you, but it's just taking it one stage further. So the last idea was about finding the paths of things you care about to improve load time. So the way you can extend that is not only find the paths of things you care about, but actually doing processing on the things you care about every frame. And so here's some examples of the kind of things you might want to do. And all of them have the flavor of find all the X and do Y. So find all the physics meshes and do physics. Find all the render meshes, do rendering. And this is a demo I'd like to show you. So this is 20,000 USD prims being updated. And let me see, on this laptop, it's probably about 110 frames a second. And so that's using this new API. And the computation can be done on CPU or GPU. I'd just like to show you how the API for that looks. So on the left is the traversal that you would normally do. And on the right, this is how you select prims for processing every frame with this new type of processing. And just to reiterate the point, if you're looking for 100 cubes using a traversal and you've got 1 million prims, it's order 1 million. But if you use Usdrt, 100 cubes out of 1 million prims is order 1. So here's a more realistic example. So this is if you're writing a physics engine. So you want to find all the meshes which have the physics rigid body applied schema. So we have this new API. It's called select prims. So the model is it's just like clicking with a mouse. You select what you want to process. You define a kernel that you want to apply to the things you've selected. And then at the bottom, show how you actually apply it. And this is in Python, but we have the same thing in C++. Now you'll notice there's a parameter there saying device equals CPU. And this is the magic trick, because if you change that to CUDA, magically, the whole thing, including the Python, is running on the GPU instead of the CPU. And this capability is because of NVIDIA Warp, which provides us the ability to run Python on the GPU. And that's by Miles Macklin and his team. OK, so once you've got your data into Fabric using Usdrt or Fabric's native interface, then you might want to render it. And over to Alois to talk about that. Thanks.
Thank you, Richard. That was a great setup for me. So, indeed, we want to render our data. NVIDIA cares a lot about performance. And we started the Fabrics in delegate work in order to meet the performance criteria required by large factories. So being able to visualize a digital twin of very large factories is quite demanding on resources, and we had to step up from where we were. So this is running a fairly small digital twin. Unfortunately, we have a lot bigger data that we can't show you, but this is running quite fast. So initially, when we started using USD and Fabric, we actually leveraged Pixar USD imaging to translate all our USD data to Hydra. And the thin layer of Fabric data, so transforms, some form of instancing, was being pushed to Hydra using an OmniHydra scene delegate that composed with the USD imaging to our render RTX. In the new architecture, what we did was create a new population plugin that actually translates all the USD data into Fabric. And on the way to Fabric, we actually run some extra tricks like deduplicating materials, merging meshes that are within an instance. So immutable data can be merged, and we can reduce the prim count of the Hydra scene at the end. We have a USD notice handler that also ensures that the Fabric state is consistent with the USD state. So anything that mutates USD would be reflected in Fabric right away. Once Fabric is fully populated, we then translate that into Hydra. And along the way, we also have some tricks here. We have a geometry streaming. So whenever we render a frame, we actually sort the list of prims in order of their importance on the screen, and we stream them into Hydra with the bigger ones coming first. And that leads to much reduced time to first useful pixel on screen, which is quite nice when loading very, very large data sets. Another thing that we do is that we listen to fabric changes. So if UI or physics or some components modifying fabric, we make sure that the Hydra state is also updated. So this is a quick demo to explain more visually what happens with geometry streaming. So this is, again, the same Siemens factory. And it's running fast. It's not as big as, again, as some of the scenes we got from BMW. And at the bottom here, you can see there's a little settings that normally you wouldn't play with. But in this case, just to show the order of the prims in the scene. So saying, I don't want to see the very small prims that are really far. You can actually use that value to hide things. Playback still goes on, the rest of the scene still goes on, the USD state is still fully valid, it's just what we stream to Hydra is reduced. So to go back to material deduplication, this is something we've worked quite hard, but that was very successful. Some scenes, like Animal Logic A-Lab, have 1,200 materials. After deduplication, when hashing all those material attributes and shader nodes, we only found 172 unique materials. Some large factories, again from BMW, have 320,000 materials, and that's way too much, but we only reduced to 94 unique materials. So this reduces load time, memory consumption, is very, very useful. Another trick that we found along the way, this use case was car configuration, where we wanted to be able to switch variants very quickly on a USD stage. When a variant switches in USD, USD sends a resync event to Hydra that says, hey, every prim under that variant might have changed, and I don't know what changed, and it's up to you to discover what changed. USD imaging basically tears down the whole hierarchy of render prims from Hydra and then rebuilds it, and that can take seconds in some use cases. So what we did here is look at the new state in Hydra and compare that with Fabric, and anything that changed, we update, but we don't destroy anything that doesn't need to be destroyed, and we can maintain high performance while switching variants. This applies as well to inserting sublayers at the root and this kind of thing. It's very, very useful in authoring workflows as well. Another use case that was really a fantastic contribution from Cesium, a great collaboration with their team, was implementing the Cesium extension. And the guys at Cesium actually used Fabric and relied on Fabric's in delegate to update the data. This led to pretty good performance, I think, and really a great way to use the Fabric API. That we're quite grateful to the feedback we received and looking forward to further contributing with that. So in conclusion, what I wanted to show, you might have noticed my French accent, but I actually live in Sydney. So I wanted to see what it would take to take this overused asset of that Siemens factory and load it in Sydney. And that's the kind of thing that Cesium and Fabric allows you to do. It kind of merges multiple worlds. Fortunately, internet speeds in Sydney are not that great, so it takes some time to stream the better looking Google 3D tiles. But this is an example of where we're going. Finally, so if you want to read more, this is already available in Omniverse today. You have documentation, example, a link to the Cesium code. The Cesium source code is actually a great example of how you can use Fabric APIs. And I will now let Toby discuss fabric lanes, which can help us go even faster. Thank you.
All right, so first of all, thanks to Richard and Eloise for being awesome. Also, thank you all for hanging out to this point of the day. And I apologize, because I'm like lower down in the stack at Nerdy, so I don't have lots of cool, pretty pictures to show. But like, we'll try and get through it. So we're going to talk about what we call fabric lanes, which is basically ways, like we talked about Omniverse as a runtime and being able to build applications on top of it. And so fabric lanes is like one of the things we're trying to expose to make it easier for you to build what you need to do and make it go fast. But we'll start at the beginning with like a simple example, because I'm kind of a simple person, and if it gets complex, I fall apart. So Richard, a long time ago, started this fabric project, and we have these awesome things, and we call them caches mainly. So the chunk of fabric data we talked about that has data from the compose stage, or even possibly other data you might want to put in there, you never need to go back to USD, it's just runtime stuff, so you throw it in this cache. And I've got two chunks of things that talk together, like Richard talked about, these framework components. I've got two sim components, and I've got a render component that's going to do really pretty stuff with that, like you saw. And so the simplest way I can imagine doing this is go, OK, I'll run the first sim chunk, I'll run another sim chunk, I'll run a render chunk, and then we're an application. So we're just going to keep doing this over and over and over for forever. These little T's, these are like real world time. I try to keep the boxes to scale. Like any errors in the PowerPoint are mine, for which I apologize. I'm not very good at this. So we kind of do this over and over again. And this is great, but like I want stuff to go faster. And I'd love to say, hey, after I'm done with my simulation, I start rendering, but I could start running some more simulation while I'm doing rendering. And you'd say to me, Toby, I'm a game programmer. I've been doing this a long time. It's called double buffering. I would go, you are correct. So I'd say, OK, cool. We'll throw this other render cache in there. And you probably would say, I don't need all the data from my sim stage to run my rendering. I need some subset of cool stuff. So as part of our API, we have this thing called this filtered copy. So you get done running your first sim chunk, you run another sim chunk, you run this filter copy, get the data you over there really quickly. Now you can go back to running your sim, and you have your render running asynchronously. And the world is awesome. And as you can see, I've squeezed more data in. I'm going faster. I'm pretty happy. But I'm not a great programmer, so I might have written some of this rendering code. And it's not always going to run the exact same amount of time every frame, or you might have added a whole bunch of new data, and it's going to take a little longer. And now everything's going to slow down. And so we'll go, OK, cool. Well, instead of having just one render cache, what if we had multiple render caches? So I just threw another one in there, and that allows me to have these slower renders. Sims can write, and that one can get done. Well, it can write for the next one, and it can be reading back, and things can catch up. So this is pretty awesome. So now I've got like a sim cache, and I've got what we call a ring buffer. And this ring buffer can be kind of configurable length, make it as long as you want. And another use case we see a lot, especially in our like self-driving cars, is like, OK, I've got this one thing that renders like LiDAR at one rate, and I've got another thing that runs at another rate, and they might not even be lined up within my simulation. So I'm running like sim at 60 hertz, and a render at 30 hertz, and another at like 13.42586524 hertz for some awesome reason. So like, what do we have to make that easy to do? So one of the things we come with is this API, which basically, like, I have this render 0.3 that happens somewhere between 0 and 1 frames. So those both have to run. And it's a very nice, convenient API. You just say, I want the time at 0.3, and it'll grab the right slots in the ring buffer, and it'll actually do linear interpolation for all the things you care about. So you've got like matrices and stuff that can be interpolated, great, and then you might have like bools, which can't, so we'll just give you back both bools. And we'll worry about like, oh, this data on this frame and not at this frame. So like, just trying to wrap all that up to make it very easy to use. And so all you think you have to worry about then is my ring buffer long enough for all of my renders? So that's great. The rendering is super happy and taken care of. I'm running my sim. But then I might say to myself, oh, I should back up and say, so this kind of concept of a simulation cache for the ring buffer, that's what we call a fabric lane. And it comes with a whole bunch of APIs to make it convenient to use. But what if I wanted to have lots of sim running at a different rate from the other sim? You would say, Toby, why would you do this? One of the people who said this to us was like the VR people. So I'm not an expert in this, but my understanding is you want to definitely make sure like the hands and the camera and that's updating at a really fast rate, because if it doesn't happen at the right rate, things get really confusing and people start to feel not very well. So we have the ability to have multiple lanes happening at the same time. And then we provide APIs to bring those back together. You can imagine, as you awesome USD people, there's multiple render delegates or scene delegates to feed the render delegate. Thank you, Eloise, for giving me that look. And now we can really start to squeeze lots of this data together in lots of custom asynchronous ways. And so our goal is to provide a really nice framework to allow you to put all of that together. And no pretty pictures, I'm very sorry. OK, so we talked about lots of stuff, and we talked about learning lots of cool stuff, and we talked about communicating through data. And if I was you, I would be looking at me and saying, but Toby, you're putting a lot of pressure on making this stuff be really, really quick. And so I'm just going to take a quick tour through some of the things that we've been working on in the Fabric area to allow us to do all those things really quickly. I'm going to go back to simple again. Suppose you just had a USDC and you had just one car in there, and lots of cool, pretty stuff you do with it. So I drew basically a simplified version of what the USD stage would look like. And the important thing to know about in there, and I'm not allowed to go past this line, is that the thing I care about is updating that little X form up there under the points for the car. I don't care about the X form for the door right now. It's not opening and closing. So I'm going to go over there. I'm going to say, cool, USD, give me that X form. I'm going to go update that data, and that's great. What if I had lots of cars? And this isn't lots of cars. But this is about the amount I'm willing to copy and paste before I get tired of working on the slide. And now I've got to go off there, and if I was going to do it by hand, I'd be because this is about the hand size, I can handle OK, there's an X form there, and there's one there, and there's one there. And that's kind of what your computer's doing if you're really working directly against the USD stage. You're going and finding all these individual things, you're updating them, and you're moving on. But if I've got millions of cars, that's not going to be very efficient. It's not going to work great on the GPU. So the idea of core you had to think about is Fabric's OK, cool. Let me go get all those X forms with all those cars, and I'm going to line them up in memory next to each other, because that's probably a really convenient way to compute it. And so these columns are these attributes, and these rows are going to be the prims you care about. So there's car 0 and 1 and 2. And we're going to do this for everything in our USD stage. And that's super cool, and that's awesome. So it's this columnar DB representation. But we don't want to lose the fact that this is still USD. So these rows are always going to be the prims, and these columns are always going to be the attributes. So we're going to hold on to that. That allows it to expose it back up to the other convenient APIs. So breaking down one more level, this nice contiguous chunk of memory, we call this a mirrored array because Richard basically invented it and called it that first, and that's never going to change. So it does a lot of cool stuff, but one of the things it does that's really convenient for us that we usually get a lot of work out of is because we have this, you saw that cool slide earlier, it was I'm going to go from the CPU to the GPU automatically. We've got to make sure that we know what memory is where. And the mirrored array kind of wraps that up and takes care of that for you. So we start out in the beginning, we're OK, cool, load a bunch of points in a nice array onto the CPU. And Fabric knows there's a bunch of GPUs out there. But it knows right now the data's been loaded there, there's memory available, and that's where the latest source of data is. So if you come along and use our read API, you might be hey, I want to read this on GPU 1 and 2. And Fabric will go, cool, it'll move some data over there, and it'll give you back a pointer. You can access it, and Fabric knows, OK, the latest data is in all these places. If you ask for it, everything's good. Then you might come along and use our write API and be hey, I want a writable pointer on GPU 3. Fabric will do the stuff to work, say, cool, move the latest data there, give it back, and I know there's memory for it over here, but I know it's stale. And if you want to get it back, I can quickly copy it, but I want all that stuff, tracking that, managing that if you've written a bunch of code. That's the annoying code. You don't care about writing that. You want to write all the cool stuff you want to write. So we're just trying to wrap all that up and provide it for you. So now I have lots of, I've told you it's a columnar database. I've got lots of rows. I've got lots of columns. I've got lots of different types of stuff. It's spread out all over the place. OK, but what would be a convenient way to access this? So we have what's called the batch API. And that's kind of what's behind the cool stuff that Richard showed about applying these kernels to it really quickly. So at a high level, what does a batch API let you do? Well, it lets you come along and say, hey, I'm going to use a batch API. Give me a Fabric. I want to use this stuff on the CPU. I want to use this in the GPU. I've got some columns. Name this. I want these guys as write. I'm gonna get these guys as read. And you hand it to this generator, and it basically comes back and gives you a view. And why would you do this? We find, if you go back to my silly example, we do a lot of things over and over and over again at 60 hertz or 120 hertz or whatever it is. And so this just generates this view that wraps all this up, so you don't have to go find all this data. Because even just finding memory can be, not free. And so once you have it, we're trying not to be opinionated exactly about what kind of threading system or what model you're doing. So basically what the view does, it gives you back this generated view, and you might be cool, I've got a bunch of CPU workers, and we've done things, if you've used anything like TBB or something like that, you get back slices and chunks of work, and you hint for us kind of how you want it broken up, because I don't actually know how much compute is going to happen in your kernel before you tell me it. So you tell me like, hey, chunk this up into about this amount, and we'll give it back, and then it'd be like, and you might be like, the CPU stuff works, and then you go run it on the GPU for processing after that, and Fabric will move the memory back and forth because of these mirrored arrays. You don't have to think about that. So did we do a good job with our batch API was a question like we always ask ourselves. And so the thing I always like to use to confirm stuff is Saxby. I'm getting old now. I've been doing this a long time. And I feel like the first time I wrote Saxby was like 20 years ago, back when I was trying to write multi-grid on a GPU. And so we have 2 versions. Obviously CPU and GPU. So like basically what we did to confirm it was we implemented it on CPU as well as we could. We wrote it on GPU using CUDA. We used someone else's library, CU Blast, and we kind of just said, what's our overhead? And there's like 2 things to pick from here. The first thing is that, like, as you know, and if you want to talk more about this, Richard, expert in all this, but like if you run stuff on the GPU, there's a fixed cost. You're going to pay it. And if you run on the CPU, it's going to be quicker until things get big. And so all you should probably take away from these is the overhead of using our batch API is pretty small. So if you're trying to run lots of things really fast on top of our Fabric stuff, you can probably just start there and use that until you find some profiling that tells you better. But like, it's pretty good bandwidth stuff for us. So the next thing is like, you're like, great, Toby. You got all this data in columns. It's all lined up. But like, I know that I want to do something like update a transform hierarchy. And that's going to be based on the scene hierarchy that you're probably going to get from your USD stage. And I'd still like to do that quickly. And this is where I'm not going to have a lot of slides, because they told us 40 minutes at 4 o'clock on Wednesday. So I should probably get through it quickly. Suffice to say, I'm happy to chat more about this after if you want to. But like, we have a system where we basically represent the scene hierarchy, our own custom memory model that's designed for allowing us to traverse these columns quickly. And one of the cool things about it is it automatically reflects between CPU and GPU. So you can do like hierarchical GPU traversals to do things like update a transform hierarchy. The last time we did this and poked it was a little while back, but we had like, I think 1.7 million prims in our stage. And to rip through them on a 3090 was less than 1 millisecond. So that was pretty fun. And so that stuff is all coming. Alois knows better than me, but there's a version that's coming in Omniverse pretty soon that I'd be excited for people to play with. So the other thing you should definitely poke at us about is like, you're like, hey, Toby, remember all these Fabric lane things and all these copies and all this data and these different things? Like, that's a lot of copying and a lot of memory. What are we doing for memory pressure? If you all use USD, you know USD has really great copy and write semantics for data. And no surprise, we do a bunch of stuff for our mirrored arrays for copy and write semantics too. So if you have your cars and you make a copy of a bunch of your cars, obviously we don't have to copy the data, we just leave it lying around. If you go edit one of those pieces of data, then these regex forms, I try to make it clear, like, that's just an array. These points ones are actually arrays of arrays. So without going too deep into the inception thing, these arrays can also store arrays in them. But for something like points, that's just meshes. And so until you start deforming stuff, you only want one copy of those. So you have copy on writes of copy on writes. It gets really complicated because you also have copy on writes across CPU and GPU. But suffice to say, we put a ton of work into this. Most of it's doing pretty well. It also has to be thread safe because of all that fun stuff. So it's just spending a lot of work to try and once again do that. So like, if you're using it, you don't have to worry about the memory pressure. We'll do the best we can to help you with that. So there's a lot of data, and it changes a lot. I just wanted to put this slide in here to put a call out to the awesome folks at WDAS who put a ton of time and effort into this USD notice framework. So if you're working directly against the USD stage, please go check this out, because it'll really help you write performant code directly against the USD stage. So we have our own change tracking in Fabric. So once again, we've got all this data. It's laying around all over the place. How am I doing on time? Oh, doing great. There's lots of things. So we have all these components, and they all want to track changes. And one of the things we say to them is like, OK, you're rendering. You tell us which things you care about, and we'll track them for you. And if you remembered, like we talked about having lots of things that render at different rates. So you register your listener, and we'll track the data for you and we'll give it back to you when you ask for it. So basically you say, hey, I care about this, and you come back to say, hey, what's changed since I last talked to you? So for each component that wants to register with us, we tell you what's changed since you last talked to us, since we don't assume we know the rate anyone's talking to Fabric. OK. So we talked about making things go fast on one node, how these components talk to each other. I'm going to talk really quick about how we deal with scaling, or what we're doing to make scaling work really well for us. So I made smaller boxes. We have your application code. You have this columnar database idea that is Fabric, and then you have USD, which you feed into it. And that works really well, and that's just do lots of pretty stuff at scale, and things move about, and it's really awesome. But the question we ask ourselves is, OK, I have this scale of stuff. What if I have this scale of stuff, right? And that factory's still there, and it's sitting down in that thing, but I want all of this to run at real time too, and I want to be able to code against real time and make that work. And if you went to the keynote, which lots of people raised their hands, so I know you were there, you saw Jensen talk about all this cool hardware we have available to us. So what do we do to make this hardware work really well? So we take this thing, and instead of going directly from USD into Fabric, we have this concept out called a Fabric service. And this is basically a separately scalable set of components that you can take your USD data and put it into, and then you can use that to feed your Fabric cache directly. So the first chunk that we have to do this is this concept of data nodes. So if we talked about this in-memory representation of this columnar data, turns out that's really well suited if you want to make that scale up really wide. So you take your USD stage, or maybe your many stages, or even whatever else you want to feed it with, and you transform it into these data nodes, and now you have this scalable set of data that can scale not only for size, but also for if you have tens, hundreds, thousands, tens of thousands of little application nodes wanting to talk to it, allows us to scale up in that way. But if anyone here has tried to do multi-node stuff with USD, you'll notice, remember, we don't want to lose the fact that these prims, which are actually mainly really strings in my brain that represent these paths, they're not stable across processes from USD. And also strings aren't efficient for sending around the world. So the first chunk we provide is this thing called this token service that allows us to take all these and provide these scalable tokens you can use everywhere. So yes, these rows are still prims, but now we just have tokens we can move around. That's scalable, it's stable, it's fast, it's awesome. So, oh, geez, yeah, bad columns, I'm sorry. So the first thing we provide with it is this idea of a column index. So you're like, OK, I call it a column index. You're like, I care about attributes of this type, or cars, or physics prims, or that. You don't want to go talk to every node in a distributed system to ask that question. You ask the central column index. It knows where the stuff is. It'll tell you about it. And then once you know where it is, you talk back and forth to that directly. You need a scalable change tracking service. Change tracking is hard enough on one node. Now everyone's making different things at different times. How do you provide consistent views? And like once again, the same question, like what's changed in this whole data pool since the last time I talked to it? So we have a service that talks to all the data nodes that aggregates that for you. So you take that, and then you still want to do hierarchical queries against it. So then we have a custom node which takes care of looking at these very large hierarchies, asking what's changed in the hierarchy, and putting that together. The other thing which we see a lot, which is actually really fun, so we have another chunk bitten for that, is this spatial index. So you might say, hey, I care about all the cars over here, or I care about all the sheep over there. And so that has to talk to all the stuff and gives you back the list of tokens. You take those tokens, you go back and talk to the data nodes, and they load it for you. So if all of that seemed crazy, the idea many is just like, OK, you really had this cool thing, and before Fabric, you just directed USD. You can do the same stuff and talk to Fabric, and it can come from this big data pool, and it'll just take care of loading it. So you can still write your code the way you used to write your code, which is like, I know there's a cache here filled with the data I care about. I compute against that, and I can worry about the larger scale another way and kind of outsource that. So that was a lot. And there wasn't a lot of pretty pictures, and you guys have all been awesome and stuck around. I know after this, there's some open office hours to talk with us about USD stuff. Please come talk to us about all this nerdy stuff. It's really fun. I really appreciate you. And thanks again for my co-presenters and all the people who couldn't be here, and for my bosses and their bosses who let me do all this fun stuff.